So here tau t is the image of t. So here I am putting 2 here, sorry, this is the dagger. Image of t under the map Hilbert-Schmidt operator to H tensor H. So I look at it for a given Hilbert-Schmidt operator as an element of the tensor product of H with itself. Now, and delta GT, whose sort of adjoint it is defined as I had given earlier. Let me see. Yes. For any orthonormal basis chosen in the base space complex conjugation. This I mentioned last time. Yes, but because of the bar here, it is there, you don't take the complex conjugation. Yes, you are right. This bar, yes. So it is the adjoint which is more complicated. This is well defined for every bounded operator T. So this is just a remark, but ultimately you have to take the adjoint. That's why we give it up and restrict to B2 of H. In order to have an adjoint in the Fock space, you need to restrict T to Hilbert-Schmidt. So these are the gross Laplacian. This is the gross Laplacian. In contrast to lambda operator, which is also important, I forget, I think. Okay. In particular, if you take identity, no, this is well defined for B of H, but its adjoint is not, it does not have an adjoint in the Fock space unless T is restricted to the subclass B2 of H. And in which case, its action is this.
Okay. So you mean that the operator delta GT when T is not as Hilbert-Schmidt is not closable, or you mean that the adjoint does not have a dense domain?
Does not have a dense domain. So this is, as you can see, is equal to AI dagger AI. The double sum becomes one sum. And this is a very well known, well studied operator. I will make some comment about it later on, that this is what, that's why it is called number operator sometimes, as I also mentioned that. And that word number operator came from this particular form because what is the spectrum of this operator? This is a sort of at least formally self-adjoint. Actually, it is self-adjoint. And you should do a small calculation to determine its spectrum. First thing you notice on the vacuum, so vacuum is often written as E0, which I forgot to mention, because this is clearly the vector 1 in the first component and 0 in all the rest. Remember the definition of the exponential vector? The first component is always 1, then f. F is 0, therefore all its tensor powers are 0, and so on and so forth. So what happens to this? This is 0. Okay. It annihilates the vacuum. Okay. But next one, so you can determine this, actually quite easy to determine this spectrum. The spectrum is the all natural numbers actually, sorry, and 0, union 0. So it is discrete spectrum, and the 0 is the only one which is simple. All the rest are of infinite multiplicity. So except for 0, E0 vacuum, which is singleton, rest are of all of infinite multiplicity. So its spectrum is sort of, it is a discrete, it is a point, it has only eigenvalues, and unlike the other one, so that's the, so this also can be thought of as a Laplacian, as I told you, but they are very different in character. Sorry, yes, you are right. The reason for this is also should be because you remember I did mention to you that AI or AJ, let's say, is, I forget, maybe minus I, T inverse, where T is the map taking identification map, I forget, it is the other way, for L2, but mu is the Gaussian on L2 of R, on R. Okay. So this is just the identification map, and T is the multiplication of, so this is the, yes. So you can see how to embed this in this just by the inverse of the Radon-Nikodym derivative square root, okay, namely the density, the Gaussian density, which is non-negative, so it is invertible everywhere. And if you compute this, this will look like this. Multiplication by xj. I may be wrong with the sign. So AJ dagger AJ is minus PJ, oh sorry, the Laplacian in the jth direction or the second order derivation plus multiplication by xj square. Plus 1, okay, plus 1, I think there is a scalar. Each of these have spectrum natural number, I mean including 0. That is in L2 of R. So you see, we have sort of in principle we have reached something on R infinity, in the sense that I have j, I am running from 1 to infinity, okay, the coordinate directions, j from, because I have taken Ej, the basis vectors in orthonormal basis in the base space H. So each of these j designate are associated with the jth direction in the orthonormal basis choice, and there you have the xj is the corresponding variable, let's say. I mean, actually there is no real variable, but I have made a mapping, so with that you can identify with that variable xj, and this is the differential operator in that jth direction, and you have an infinite collection of these differential operators in each of the j directions, and each of them has discrete spectrum, natural number and 0. So it is sort of putting together all these. So this is the what we may call R infinity, and but only thing we have done is that this measure mu, this is for each direction, okay, R, that means jth direction. So you will have Gaussian measure in each of the jth directions, but Gaussian measure, when you put them together, okay, in each of the jth direction, that will not extend to a Gaussian measure unless you do something more. Okay? And that something more is being done by these operators T, etc. Okay? It has to have something extra property. But we won't need that, so we will just proceed. So let's remember this is the beginning definition of the gross Laplacian. So the difference is just that aside from this complex conjugation, it is just that there is no creation operator here, just both annihilation. But its adjoint will have then both creation. In other words, formally maybe an empty bar.
Just a clarification. So this AJ dagger, AJ also has its spectrum as a natural numbers union
as in L2 of R for each j. And this is a very well known and well studied operator. But there, as I said, the gross Laplacian is well defined on exponential vectors, but its adjoint may not be well defined. And in order to make it well defined in Fock space, I impose this. If I don't have this, then the adjoint of course exists, but you will have to restrict, you will have to enlarge the definition, or the space has to be enlarged. Okay. So I don't want to go into that, I want to do everything in Fock space. Now, having said that, now I want to go to the next step, is to do the integration theory, etc., just as Hudson Pathasarathi did. So that part I want to save time, I want to use some of my old transparencies, because that talk I have given literally infinite number of times. So if you would excuse me, I will just use the transparency for that, in the sense that I will recall what Hudson Pathasarathi did for the first three processes, A dagger and lambda. And I will add the gross Laplacian as the fourth object. And then we will see how that theory has to be modified and what comes out of it, etc. So for the first part, I want to use the transparency quickly. So there will be some repetition of what I will, oops, what happened? I think the light has to be switched off somewhere. Yeah, I think you can see it more or less. You see what you see, rest you imagine. Okay, so this is again repeat, okay. Ignore the probabilistic comments, they will be there. So this I have already mentioned. So this page ends with the exponential vectors, which I have also mentioned. Okay, so this I have mentioned, so I will quickly go through it, and you can see the exponential property, and then so we will make L2 of R plus as the base space in due course. This is a probabilistic comment, you can ignore if you don't like it. This says essentially, it is an important and interesting observation, that the Fock space is isometrically isomorphic to L2 over paths, continuous paths from 0 to infinity. Okay, L2 over paths, that means your variables, independent variables is not x1, x2, xn or anything like that. It is a continuous object, okay, the independent variable over which you are taking L2. So the measure is the next thing that comes. How do you put measure, or what measure do you put on these continuous functions? That is called the Wiener measure. That is the measure that we use. P is the Wiener measure. This is the continuous functions on the right half line 0 infinity. Okay, I should have said it beginning at 0, but that is not too important. And then certain kind of objects living here, if you take their inner product, so you see that's an L2 inner product on the left hand side. On the right hand side is the Fock space inner product. They are equal. Therefore, as Hilbert space, there will be an isometric isomorphism coming up, but you can ignore that. Now, I want to have the what is called the filtration. So, for that we observe that once you have restricted the base space as L2 of R plus, then you have a natural order on the real line, and L2 of R plus can be thought of as L2 of 0 to t and L2 direct sum L2 of t to infinity, right, for any t. When I exponentiate it, the direct sum will go over to tensor product. Okay. So, that is what is essentially stated here. So, this is a notation. Notation is the Fock space over the base space which is L2 of 0 t. So, there is a t index sitting here, and this one is the Fock space over t to infinity. So, this is like you will call it the past, and this you will call the future. So, past space versus future space. Then you can easily see more or less by what I said that the total Fock space is unitarily isomorphic to this tensor product. The past Hilbert space, past Fock space, and the future Fock space. But this happens for every t, and this is a major property of the Fock space, that this is called continuous tensor product decomposition. For every t you can decompose it as past and future. Okay. In particular, this is achieved by essentially observing this, that you take an exponential vector corresponding to the base vector f, which is a function now because base space is L2 of R plus. So, f is a function. So, here look at them, they are very attentive students. So, E you just chop it off with the characteristic function 0 t and here t to infinity. So, the identification or isometric isomorphism comes from this observation. Okay. So, we write, so for us now I will introduce, because our main aim is to solve differential equations. You see, one of the main aims of doing integration theory, so that you can write differential equations. You probably don't recognize it, but think back. That is the reason for doing integration. One of the reasons for doing integrations is to invert the process. Okay. So, that is what we are going to try to do rapidly. So, it is convenient to introduce another initial space. Now, here the notations were different, unfortunately. So, here I have written, where is it, up there, H. Since I have already another small h which is the base space, so think of it as H naught or some other notation. Okay. So, H is factorized. So, this is the past space. So, the initial space, this H is called the initial space. H tensor gamma t, this is the past space, and the future is just gamma t. Now, look at B sub t, which is all bounded operators acting on this thing and identity in the future. Okay. So, you have a family of operator algebras. Okay. Von Neumann algebra, for example, this is a very special von Neumann algebra sitting inside these. You could have taken more general von Neumann algebra, but here we will stick to this large von Neumann algebra. This is an increasing family. As t becomes larger than t prime, then B of t contains B of t prime, and so on, with the B infinity being B of H tensor Fock. So, this is called a filtration. Okay. In the classical case, people who are accustomed to a little bit of probability will recognize in the classical case you will take a commutative von Neumann subalgebra of B of Ht, okay, and that will be increasing, and that will give rise to a classical filtration. Here we have just thrown away the commutativity, just as Somalyo did in parts of his lecture. Started with functions on the group, which gives you a commutative algebra, but then you throw it away and look for more general algebra. Something similar philosophically. So now, since we want to do integration theory, so I am revisiting Hudson Pathasarathi from this point on. So you look for, because you want to catch a large set of objects, so you want to keep it as flexible as possible. So look for a subset of the initial space D0 and another subspace of the base space L2 of R plus. Now I have chosen the base space L2 of R plus from now on, and characteristic. So in such a way you choose this subspace such that this is invariant under the projection to any of the projection onto any of the subsets of the real half line. Then you look at this. D0 is the dense subset in the initial space. E of E we will already have introduced the exponential vectors. Now E of F will come from this special subset. Because I have chosen the base space as a special space, so I have possibility of restricting things a bit more according to my convenience. Okay. So I choose exponential vectors, a linear span of exponential vectors, each of them coming from a subset like that. And then now we are starting on the path to doing integration. So you are given an T-indexed family of operators in the Fock space, okay, such that, well, where is it? It is somewhere, okay, here. So xt has the following property. If you take the element xt out of this collection and let it act on a vector like this, I have removed the tensor product sign because it is implied, but I won't write it because just too much writing. Okay. So what is u? U is a vector from the initial space D naught. Yeah. Oh, okay. You want upper. Okay. Yeah. All right. So you choose U from D0, which is a dense subset of H, the initial space. F is in this good subset M. So look at tensor product of these vectors and let xt act on it. It stays in Ht, that is, it stays in the past. That is the hypothesis. This hypothesis comes from again probability theory, motivated by probability theory, but here we will not worry about it. So that means what? That means this. So this rewrites this in more details. Look, in the future it does not do anything. It leaves the E of F. F super T, remember, is F times characteristic function of T to infinity, that means future. So that this immediately says it does not disturb the future, it only acts in the past. Okay. So this family has very special behavior, namely it only affects the past and not the future. Such family are called adapted, that is the name taken from probability terminology. That is why it is said to be adapted. And domain of xt has to be this so that I can make this application. Okay. That is just anticipates this to write this. Okay. This just says what I have already said. Okay. So do you get it? So for every t this happens. This is a very strong requirement. It is not just that it happens for one t. For every t, as t changes, the xt's action as t increases, xt's action expands, namely more vectors come in, more components of the vector comes in, but it leaves something untouched still. Okay. So this is a very strong requirement on the such functions, and such functions will be my candidate for integrand. Okay. So these integrands will have this special feature. Okay, this again repeat because, as I said, this is come from some other talk. Now we also require this to be strongly continuous to do the integration theory. In other words, we will try to do essentially some kind of a Riemann integration. So for which Riemann-Lebesgue integration, which we would like to have some continuity. So this map is taken to be continuous for every U and F. That means it is continuous on a dense subset. Such things are called regular. So our integrands will be so-called regular processes. Now these we have already gone through, so I don't get, and these we have already gone through, so I just remove. Now there is a word martingale which I will try to explain. This is again, this word has come from probability theory. You can ignore it for a moment. So these are the special operators which we had already introduced, but now these are the special t-index processes A chi0 t. Remember A of f we had defined for every f in the base space. Now the base space is L2 of R plus. I take in particular the characteristic function of the interval 0 t, and that A is called capital A of t. Now it becomes a function of one real variable, right? Operator valued function of one real variable. Operator valued function when the operator is not defined everywhere but only densely defined. So it is a densely defined operator valued function of t. Similarly here I have done nothing new, and similarly lambda, but as I said last time, here the characteristic function is taken with a different role. Characteristic function in L2 can play two roles. One is an element of the vector space itself. Other, if you think of it as a multiplication operator by the characteristic function, then it is a projection operator. Okay? Got it? So here the second role, when I compute lambda, remember here we had capital T, it is still there in that board, lambda of capital T. Capital T is a bounded operator in the Hilbert space. So there I put capital T as the projection operator to the range which has chi0 t times something. Okay? Okay. Then it is easy to verify that these satisfy the hypothesis that we had given earlier. Okay? Of course, these do not have anything to do with the initial space, remember. This is only in the Fock space. That is why we defined it. And there they are adapted. Martingale I will come to later, so ignore it for the time being. Just the last page. Oops, or page before last. These three. Okay. Only here D0 does not play any role because these things have nothing to do with D0 or the initial space H. So you can ignore the D0 part. It is identity on D0. So that does not play any role. Rest of the things are satisfied for these three objects that I just showed. So they are all regular and they are also martingales, but which I have not defined yet, so I would come back to it a little later. Okay, there is something more which I do not want to say, so I will just. So I will quickly go to the integration theory based on these objects, which is what Hudson and Pathasarathi essentially did. There are some more complications you can introduce, but that is not of great interest. Instead of L2 of R plus, you can introduce multiplicity and so on. You can take L2 of R plus taking values in some another third Hilbert space, okay. But that doesn't really change the structure fundamentally too much, so I would refrain from bringing that in. Okay, so how do you do integration? So let MT be any of those three basic objects, A dagger, lambda, okay. So lambda of the characteristic function 0t as a multiplication operator is written as a capital lambda of t. It is a notation only, okay. Now comment, go back to the right hand side of the board. I had said AJ dagger AJ, or rather, yeah, here. The spectrum of lambda of I is of this kind. So lambda of t, what I call now capital lambda of t for every t, is also the same. For every t greater than 0. Because this is, what is this? This is living only on the sector HT, and in future it is identity, okay. So you can forget that, okay. And up to HT it is just like this, because characteristic function is just the identity in the sector up to t. So its spectrum will be the same, but in HT only. Oh, sorry, there is no initial space is necessary. For every t, it has this discrete spectrum, okay. Or not discrete, point spectrum. There is a difference between point and discrete spectrum, okay. Usually the word discrete is used by analysts or operator theorists when the multiplicity is finite, okay. But here multiplicity is infinite, so it is just point, just eigenvalues. And that property is what was used by, well, Hudson, Pathasarathi and others to model, it is automatically there essentially by the structure, model what is called, probabilists call Poisson process, okay. Counting process, because this is a natural candidate for counting, okay, because it has spectrum just 0, 1, 2, etc. So people who know Poisson process will have heard the counting process. Okay, now next thing is the so called, okay, there it is, okay. Now observe, so let M be any of these three so called basic martingales. The word martingale just ignore for a moment. Then you observe this quite easily, that let MT minus MS, where M is any of these three, acting on an exponential vector, will have the following property. Notice it is a additional property, not just adaptedness, what we call adaptedness. The part up to S gets unaffected. The part which gets affected is only the part S to T. Oh, I didn't switch off my mobile. So some advertisement, I guess. Okay. So that means, and the future is anyway left unaffected beyond T. So that means the effect of the increment of these objects is neither in the past nor in the future, but in the middle, okay, S to T, okay. Because remember, what is integration? Integration means you have some kind of a function and you are putting some kind of an increment over the next interval, let us say, and summing over this, that is the Riemann sum, right. So I am trying to now look at the increment part. So this is the increment part. Here the additional feature of these three integrator is that they live only on the part where the increase is taking place, namely S to T, or change is taking place. It does not do anything in the past, does not do anything in the future. Such a thing is called independent increment process. It is independent of the past, independent of the future. So such things are independent increment. And when we add the gross Laplacian to our list of integration theory, unlike the first three, this will not have this property. So it is not a what is called a process of independent increment, but it is a Martingale. I will come to the Martingale part again. So here is the first theorem, if you like. So how do you do integration? Here you do exactly the way, you mix up a little bit of Riemann and Lebesgue, okay? So you take simple functions, okay? What is a simple function? So I will use the board for a few minutes. Oh. So how do you do integration? Yeah. So take xt to be a finite or infinite sum, xtn well, I should have probably another name here, LTN, characteristic function of Tn to Tn plus 1. Simple function. So this is a fixed object to the left. So you have taken, so Tn plus 1. You take the coefficient at the left hand point. Notice that is very important here. The coefficient is taken at the left hand point. Increment is over this part. Okay. So that is my simple function. So this is a simple integrand, okay, the candidate for integration. So you define, let's say, so this, like Riemann integral, you see I am mixing up Riemann and Lebesgue because I have taken this kind of thing which is more, smells more of Lebesgue integration, but nevertheless I do it only over finite time horizon, okay, unlike Lebesgue. So let's say xt a dt. A is that object I defined. This is a of characteristic function 0 t, okay. To remind you again, for every t it is a family like this. I take increments of a dt means increment. So what is this? This is trivial. So this is a definition from this, for this simple function, the sum over LTN, and here you will get a Tn plus 1 minus a Tn, right? The increment of a over the partition Tn to Tn plus 1. Right? Yes, it is an operator. This is the, yes, this is all simple things are like that. Simple function is you take a value. Here the value is an operator. It is an operator valued function. Okay, that's all. Usually you will take complex or real or whatever the case may be. Here it is an operator valued function. That's all. Nothing has changed, except that of course these operators could be unbounded, okay, but that one has to face as the case may be. And this sum also has to converge in a suitable sense. So usually this is defined on such vectors. So you will put So how will this, let me wipe this, maybe I go there. So what does right hand side? So integral, this is what I am trying to define. So as usual, best place to try our luck is on the exponential vectors. So u is in some nice set d naught. This is inside the initial space h naught, let's say. This is, or h I had said in the transparency, this is in L2 of r plus, okay? And this is equal to LTN 8 of Tn plus 1 minus ATN acting on UAF. Now U will not have anything to do with A. The initial space has nothing to do with A dagger lambda. It will come here. But part of the EF also will come here. So this lives up to Tn. Okay. So I have to put the exponential vector up to Tn here along with this. So let me put a bracket here. This is a vector. Okay. Then comes ATN plus 1 minus ATN. That acts only on E of f from Tn to Tn plus 1, which I designate that way. Upper is the left hand point, lower is the right hand point. And then, so these are all tensor products, remember, which I am not writing, just that I am getting bored. And the last part is f beyond Tn plus 1, where nothing happens, it is identity. So each piece is like that. And now you have to put them together and talk about convergence, etc., etc. And the same thing you can do for A dagger and lambda. Multiplication by characteristic function. Once you have done that, then this theorem results. This gives you, in a sense, the value of the integral. Okay. How it looks like as an operator between these two vectors, inner product acting on, evaluated between these two vectors. Namely, so well again, instead of L bracket Tn, here it is written L sub T. Okay, that's the only change has taken place. So notice the integrand is here. Okay, rest is a scalar object. One place, the first one, it picks up the right hand side. Second one, it picks up the left hand side, f bar. And third one, that is lambda, it picks up both f bar and g. Okay. So that's the characteristic of the three integrator. So m, first one is when m is a, the annihilator. Second one when m is a dagger. Third one when m is lambda. So this is a typical feature of this integration theory. Okay. And you see the difference from ordinary integration theory. The result of the integration gives you an operator, of course. You are integrating an unbounded operator function with respect to unbounded operator increments. Okay. So remember that. Okay, so that's the first lemma or theorem, whatever you call it, of Hudson-Parthasarathi. Next is the most important one. Well, there is a little bit of overwriting. This is called the Ito formula that tells you, see, previous one gave you the value of the integral. as an operator. Okay. This one tells you if you have two integrals, how do they behave if you put one after the other. Oh, okay. This is a little complicated to explain, but let me explain. So I have left hand side, I have three possibilities. There are three possible integrators, right hand side, three possible integrators. So there will be 3 by 3 matrix which will describe the result of the integration. Okay. So in that spirit it has been written. Do you understand now? Because for example, I may pick the first one here and third one there. Okay. The result will be given, the first two terms are given here with three choices. Here is the important one, where it will be, you have to choose the 1 3 element of 1 3 element, which is 1 3 0. Okay. So this is a 3 by 3 matrix which essentially sort of condenses the result of the theorem. So what does it do? First two terms you should be able to recognize easily like a classical integration theory. Okay. Essentially says the following. Any integration theory should automatically satisfy that if it is properly defined. The first two terms. It just says that's the Leibniz rule essentially, or integration by parts if you like. If you say, for example, classically think of it this way, f of t is equal to integral, what should I write, h of t, h of s ds, and g of t is equal to integral xi of s ds. Okay. What you want is f of t times g of t. Okay. You want to write it as an integral, which means you have to write integral because both are 0 at the end point. So fundamental theorem of integral calculus or integration by parts formula, they are the same thing. Prime. Then you will have one place where you will have f of t. Other place you have g prime. G prime is xi. And the second one will be just the other way. Sorry, this is a integration variable s ds. Okay, this is the, if you like, you call it the Leibniz rule. If you like, you call it the integration by parts. So first two terms. So this is the first integral times the second integrand. Here the first integrand times the second integral. And because you are dealing with operators, the order has to be maintained. You cannot mix up the operator orders. So you just see the first two terms are precisely that. So this is the integrand of the first integral. This is the integral, second integral, and here conversely. Okay, first integral and second integrand. Okay. What is new is the last one. Now these come from these numbers, I mean these scalar functions come from just the simple observations, which maybe I should have said earlier. You see, you have, so as I said, at minus as, this will come outside and acting on E of f, what will it do? We know this. What is this? This is a of characteristic function of 0t minus a of characteristic function of 0s, which you can take inside, and let's say s is less than t. Okay. Then this is right. You have the bigger characteristic function, you are throwing away the smaller characteristic function, leaves you the characteristic function of the leftover interval. This is acting on EF. What is that? That is inner product, characteristic function of ST with F. Right? That's the eigenvalue, eigenvector relationship of the annihilation operator on exponential vector. So what is that? That is integral from S to T F d tau, let's say, EF. Okay? No bar appears because characteristic function is real valued. Okay? Now, when you write it in the differential form, therefore A dt, okay, this is just a notation for this, remember, is equal to Ft dt acting on EF. I mean, this is just a, sorry, EF should have been here. This is just the previous statement restated in the so-called differential form. So that is what shows up in here, all those. You see, one of them is F bar, other is G, here is G and F bar, they change place, and here is F bar G, both cases. There are three cases, and here this is the additional term which didn't appear in the integration by parts formula. That is the new thing. That is the extra thing. And notice what has happened here. Integrand, integrand. Not integrand, integral like integration by parts formula. In integration by parts formula, in classical integration, you have one integral, one integrand, and the other way. Two integrands never will appear. Right? But here two integrands appear for the first time, and along with the scalar variable, the scalar valued functions which are displayed in a 3 by 3 matrix depending on the choice of the integrator in the two integrals. So 3 by 3. Many of them are 0, as you can see. So as soon as you have done an integration theory, the immediate, as I said, one of the aims, there are many others, is to look at solving differential equations. So and when you learn a differential equation, the first thing you try to do, if you go back to your school days, what is the simplest thing that you try to do to solve? Linear differential equations, right? So here we will try the same thing, except that everything is unbounded, an operator. That is the complexity. But we are big boys. We have learned how to handle such things. So let us not be afraid. So that is the little bit of that I will do, but I cannot. Well, my aim is to do with the gross Laplacian, but that I will try to do tomorrow. So okay, this is a linear constant coefficient differential equation. That's the simplest that one can possibly start handling. So x is the unknown that you are supposed to solve for. Now here the order matters because there everything is operator. So whether I put x here or x there on the right will make a difference. Okay, some will be more convenient than the other. So here this is more convenient. And here are so L, M, F and G are the coefficients of the differential equation, taking values. Well, here I have written, assume them to be just constant, which means they are just operators in the initial Hilbert space. I don't want to do if the coefficient operators are constant and bounded, then one can easily construct this solution just roughly following the Cauchy-Picard kind of method. That's a classical method. provided they are bounded operators, as I said. Otherwise, Cauchy-Picard fails, as you can imagine. So I will stick to bounded operators. Now you take some special choices of these coefficients. Okay, to remind you what the coefficients were, once again, this is the differential equation, L, M, F, G. Let them be constant, okay, not depend on time, and let them be bounded operators of this special form. So F is the, so let us remind you what was F. F was the coefficient of the lambda, M was the coefficient of A, and L is the coefficient of A dagger, and G is the usual dt. If L, M, F was 0, then this is an operator equation you have seen. Okay, x dx equal to x times g dt. Okay, how do you solve it? G is an operator, possibly unbounded operator. If it is bounded operator, you can easily solve it. What is the solution? Trivial. If G is bounded, it's just like numbers, you can solve it. The exponential function will solve it. Okay. But here the complication is there are many other things. So it is far from trivial even if L, M, F, G are bounded. Okay. But this case is relatively trivial, but interesting nevertheless. If you choose the coefficients this way, so F once again is the coefficient of the lambda process. So S minus 1 where S is unitary. So it is unitary minus identity. So that's a very special form of the coefficient. K is the coefficient of, I think, A dagger, which is minus L star S. S coming from here, L is another bounded operator. Okay. And G is of this special form, minus half L star L plus IH. H is another bounded operator. So here is a negative operator or non-positive operator. Here is a I times any self-adjoint operator. So this is the real part and this is the imaginary part. Okay. If G is unbounded, real complexity comes from the fact that for an unbounded operator, you cannot in general separate real and imaginary part. Okay. For a bounded operator, which you can do easily, for unbounded operator in general, there is no way you can separate real and imaginary part. But for special subclasses, you can. Okay, we'll stick to bounded. So in general, a solution will still be unbounded, but in this case, it will be not only bounded but unitary. Oh, somehow I have lost that part of the transparency. Oh no, it is there somewhere. Okay. Anyway, I have come to the almost the end. So let me tell you that that differential equation, if K is minus L star S, F is S minus identity, and G is minus half L star L plus IH, then, so remember L, what was L? L was the coefficient of the dA dagger term. Okay. Then the solution exists and unique, xt as I called it, exists, is unitary and unique. So there are special cases where you can solve it nicely, but in general you have great difficulty in handling it. Okay. For if the coefficients are unbounded, it is rather difficult and quite challenging to prove unitarity of the solution. What we will do next time is the following. So what we had done is this equation, remember dx x LDA dagger plus k f d lambda plus k dA plus g dt. This is the equation we talked about. Now we will add plus, I don't know, g or m d gross Laplacian of some with something here, it has to be a function of t also, plus some n this I would like to add further, and this automatically will change. It will not be so simple as this. What will happen, will be forced upon, is that the dt term will undergo some change. So it will be an object, you will have a g, you will have etc. Now these are, sorry, not k. So this is, it will be h a t plus I don't know p a dagger t, this times dt. So the equation undergoes a fundamental change. So Hudson-Pathasarathi equation changes quite drastically. Dt term, with the addition of this, you have to add this to have a reasonable solution of this differential equation. So the dt term changes drastically. It is not just some constant operators times dt, but it has at dt. But nevertheless, the solution is unitary. Under some, you have to of course restrict, some relation between them has to be there, but solution is still, can be made unitary under, with those choices. Okay, we'll take it up next time, the last talk.